Hi everyone. Today we want to solve this inequality. If you like to solve the problem yourself, please pause the video. Basically, the method of solving any kind of inequality that is comprised of a product of algebraic expressions or ratio of algebraic expressions is like problem 35. We basically need to find the intervals at which this expression is less than 0. And in order to do that, we break it down into the expressions that are being multiplied by each other or divided by each other. We find the roots of those. Then we find the polarity of those sub-expressions. And from there, we find the polarity of this big expression. So if I call this f of x, the first step is to find the roots of the numerator and the denominator. So 1 is 2 minus x equals to 0. So x will be 2. Then 2 is this expression, minus x squared plus x plus 2 is 0, which since a plus c is equal to b, we know that one root is x1 is minus 1 and x2 is minus c over a, which is 2. 3, x squared minus 9 is 0. Therefore, x squared is 9 and x1 will be 3 and x2 will be minus 3. And for the denominator roots, we have minus 3x equals to 0. Therefore, x will be 0. And minus 2x squared plus 3x minus 1 is 0. And since the sum of the coefficients of this quadratic equation is 0, so x1 will be 1 and x2 will be c over a, which is 1/2. Now we need to make a table, and for the first row of the table, write these roots that we found in increasing order. So if I make a table like this, and the smallest root that we found is minus 3, so this, then it's minus 1, then it's 0, then it's 1/2, then 1, 2, and 3. So then we write down the expressions that we have in function f of x. So 2 minus x is the first row. Second row is minus x squared plus x plus 2. Third row is x squared minus 9. Fourth row is minus 3x. Fifth row is minus 2x squared plus 3x minus 1. And last row is f of x. So let's just construct this table. So 2 minus x will be 0 at x equals to 2. Minus x squared plus x plus 2 is 0 at minus 1 and 2. So here and here. X squared minus 9 will be at minus 3 and 3. Minus 3x will be at 0. And minus 2x squared plus 3x minus 1 will be at 1 and 1/2. Now let's find the sign of each of these expressions. So 2 minus x, for x is smaller than 2, it will be positive. And in order to get to that, we just replace x with 0, which is smaller than 2, and we get a positive number, which is 2. So this will be positive, 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 negative, negative. Minus x squared plus x plus 2, its roots are minus 1 and 2, and in order to see what is the polarity of it between minus 1 and 2, we just replace x with a number between minus 1 and 2, let's say 0. So we will get 2, therefore it's going to be positive between these and negative outside this interval. X squared minus 9. Again, if we replace x by 0, we get minus 9, so it will be negative between its two roots and positive outside. Minus 3x. For x's smaller than 0, it will be positive, and larger than 0, it will be negative because of this negative sign. And minus 2x squared plus 3x minus 1. Outside the interval of its roots, if we replace x equal to 0, it will be negative. So here it's negative, and therefore it has to be positive between the roots. And again, outside the roots, it will be negative. So if we multiply these signs by each other, for x's smaller than minus 3, we will get positive. Between minus 3 and minus 1, we will get negative. Between minus 1 and 0, we get positive. Between 0 and 1/2, negative. 1/2 to 1, positive. 1 to 2, negative. 2 to 3, negative. And beyond 3, positive. So we want we want to find the interval where f of x is less than 0. So this interval, this interval, this interval, and this interval are the answers. Now, I forgot to say that we can find where f of x is 0 or infinite based on the roots that we found as well. So wherever there is a root at the numerator, which is these roots, 2 minus 1, 2. So at 2, this is 0. At minus 1, it is 0. 2, again, is a root, so we already had it. And 3 and minus 3. So here it's 0, and here is also 0. But at the roots of the denominator, it will approach infinity because the denominator will go to 0, so the fraction has to approach infinity. So it will be at 0, it will be infinite, and at 1/2, it will be infinite. So I think yes, at 1, it will be infinite too. So if I want to write the intervals of x has to be a member of minus 3 to minus 1, and this does not include minus 3 and minus 1 because we only want the intervals that the fraction is smaller than 0, not 0 itself, union with interval between 0 and 1/2, interval between 1 to 2, and interval between 2 and 3. Just note that although these two adjacent intervals are both answers, I cannot just write 1 to 3 because that will include 2, but at 2 the expression is 0. So we only want to find the intervals that the expression is negative, not 0. So now we can also have an interesting observation here. If you look at this table, you'll see that the sign of f of x will alternate between positive and negative every time we hit a 0. So it's positive for all of the x values smaller than minus 3. Then it becomes negative after this 0. Then it turns positive. It turns negative again, positive again, negative again. But right at this location, the polarity doesn't flip. It remains negative and then flips at the other 0. The reason for that is if I draw a general curve, f of x, this is x and this is y-axis, every time that a curve hits x-axis, which means every time that it becomes 0, the polarity of it has to change, unless there is a repeated root, which will be the case that it touches the x-axis like this. So at this point, it has two roots, x1 and x2, and as you can see, although there is a root, but the sign of the function doesn't change. So we can also conclude that if we found the sign of this function f of x for only one of these intervals, the sign at every other interval will flip compared to the one before it, except where we have a double root. Like here, we had two roots equal to 2, and therefore the sign didn't flip at 2. But every other place, the sign flipped. So this is kind of a shortcut to finding the polarity of this function at everywhere by just finding the polarity at one of these intervals and knowing where we have a double root. So this is pretty much a general way to solve problems of this sort. Again, as I said, it's the method is very similar to what we showed in problem 35. I will be posting more practice questions like this, and I hope you master this subject and enjoy it. Thank you.